Never mind. Yeah, I got it figured out. I actually just got it figured out. My apologies. I actually got it figured out. Hey everyone, how are you doing? So, pleasure to meet y'all. Today, we're going to be talking about total internal reflection. So, total internal reflection, simply put, is what happens, you know, usually we all know what reflections are. You have a mirror and you can see your reflection. You can see how this is used, every day. You see a mirror. And what you see with a mirror is you have an outside, piece of metal, usually aluminum, at the far side of the glass, and that's what reflects your image. But what about, what if what you're inside causes the reflection itself? So, in other words, what happens if, and the two things we're going to be looking at today are a tank of water and how we can actually see the reflection. You'll notice I'm pointing my laser up, and you'll see that the light actually points down. And we'll also be seeing it here in this tube, and you can see the green light shining back and forth a little bit. And we'll be able to and we'll continue to see what is it and where do we see this light behave in this way. So first of all, my apologies if I'm a little late to the streaming. We had some technical difficulties, but for those of you who join us and those of you who will join us, we'll be more than happy for you to be along, and by all means, come for a ride. So total internal reflection first came about when you saw a medium, when was actually something that was studied as much as 1200 years ago and 600 years ago. I believe it was studied in the 8th and 9th century in Islamic Spain, and then rediscovered again during the Renaissance. In fact, one of the things you learn about when you study physics, especially here at the University of Arizona, is Snell's law. And what Snell's law says is when you go from a medium that has a high refractive index, air has basically no refractive index. It has a refractive index, which we display with an N, markers, the most important thing when you're discussing physics. Oh, this is a nice marker. So what they discovered was when you came in at an incident angle like this to a medium, like this is air, and usually air is represented of just an index of 1. The index of refraction is how much of material slows down the speed of light. For example, if you had an index of 1, like you have for air, you have c, which is the speed of light, over 1. In other words, speed of light just travels at the speed of light. But if you had a speed of light, say, of 2, then you would actually be going half the speed of light in the material. So the index of refraction is what allows it to travel. And also, one of the really interesting things when you deal with light traveling through a medium is it actually bends light to a narrower angle. And so this is what you see, and so this is one of the things you see when you travel through a medium. And we'll see if we can see that here. So, give me a sec. So we'll see. So we see this going straight, through the material. But if we actually shine it through, it will actually bend light ever so slightly. And you can't actually see it, but you can probably see it let's see if I put my, one of the things, you know, one of the things that you have to practice with physics is how to display it in a way where you can actually see the difference. So you know what, let's actually try it this way. This is physics. Half of physics is figuring out how to try it another way. So, I'm going to see if I can get it. It's perfectly aligned. So you should see half of it this way and half of it the other way. So you'll see right here I'm coming at a certain angle, and this should actually straighten the beam so it actually goes in more forward. And you actually see, I don't know if you can see that, but it actually bends it a very slight bit. But actually, this is the very steep angle of my laser. This is the direction in which it comes in. However, the real question is, how can this light bend? But what happens if, say, you were to come inside a material right here, like what you see here, and then you allow it to bend. So you can see that at some point at an angle with what you saw here, that if you came in at a steeper angle, you might get something pretty much almost vertical. However, what if you were to come in at a very narrow angle in here? The thing is, it would slowly go more straight, until finally you would reach what's called a critical angle, in which all of it's reflected downwards. And what we do is we actually see that over here. So this is the part that gets fun, where you get to see the light, transform. So let's actually step back over here to this table. And you can see the rod right there in the middle of, should be able to see this rod right here in the middle of the screen. And now we're going to turn off the light as soon as I find my laser, and then turn off the light. So you should be seeing the light, me shining it over here. Now we shine it through this, and when we shine it straight through, it goes at the laser. And if we do it at a very steep angle, you need to get pretty steep here for it to not go through. But you'll find if you come in at any angle, then you'll see that it actually jumps around a lot. And one other place, and you actually don't just see this feature with glass. You also see this feature with water as well. Although water has a slightly lower refractive index. Let's see if we can pop it here. You'll see that before it goes straight, but at a certain angle, and when you do it at an angle, you see the reflection. You see it going through a zigzag pattern through the water. And it's this feature that allows the water, that allows it to stay trapped. You can actually see it. Hold on, let's actually turn the lights back on. One place that you can see it is if you ever go down to, say, a swimming pool or a lake, you'll actually be able, if you actually go into water and you sit at the bottom and were to look up, sometimes you might not actually see through the water because the light bounces back down. Now, one of the more interesting things that happens in the water when it's not clean, when it's dirty like this, is scattering. What scattering means is you have imperfections in the light. So when the light shows up, it actually bounces off all these particles inside. Now, to do this, we would need to sorry about that, I forget the screen. So you actually see when you hit the light, it bounces back. You hit this beam, it bounces back. And it keeps going forward whenever you see it in the water. So what happens when you actually see it inside? What happens when you actually see it inside? What happens when you actually see it here? Here, you may have noticed that it just kind of shines straight through. So we need a way to cause the beam to go wider. And to do that, we actually take a little bit of the paper that's actually, let's see if you can see that, that's actually right under the tank. We're just going to take a little bit of tissue paper to actually adjust this. So what you do is you take a piece of tissue, you make sure your camera is angled right at the tub, and well, first of all, you have to turn off the lights. So before, let's see. So before you saw it going straight through and it was a pretty straight beam. But if you were to put a piece of paper right here and block it, then let's see if you're able to see that. You actually see the beam actually widen a little bit, and you can actually see it right here on this side. You can see the beam widening in as it scatters through the molecules inside the water. Let's see if you can see that right there. And that is ultimately a lot of the features that we see in physics. Now, it's a really cool trick, and it's something that we've known since the 1600s. It's not, if not much earlier. But how do we use it in practical applications today? Well, we actually have an example right here. One of the biggest examples we see this is in fiber optic cables and fiber optic systems, where you can actually take a very long string of light like this and transmit a signal through the wire. So you can actually start it here, and let's see if I can line this up just right, and it actually shines through. And you can see it lighting up, and all it's doing is coming from this laser here. So let's actually turn off the lights to get a better look. And you can see it all shines. Now it also matters what the angle I take. For example, if I take a really steep angle like here, it just more or less goes a little bit, but then it shoots out. But if I can straighten it out a little bit, you can actually see a lot of them lighting up inside, all the way to the end. And this is how fiber optic cables work. This was actually discovered in the 1960s. Let me turn the lights back on. That, hey, we can take a bit of light and transfer it through. What if we could encode a signal on it? And that ended up being the backbone of the internet that we have today. Glass being immensely cheap to reproduce. and this allowed us to send signals back and forth and encode the signals with ones and zeros. And when you could encode them with ones and zeros, then you're able to communicate all throughout the internet and get signals to code them through. Now you'll notice, it actually doesn't say here, but the wavelength of green light is 600, it actually says right here, I don't know if you'll be able to see it, it says 532 nanometers. One of the really cool things about glass is you can actually have multiple wavelengths traveling through them. We call them multi-mode fibers. Though most of the internet is made up of single mode fibers because it allows them to split off in different directions. But multi-mode fibers, what they are able to do is take multiple signals, like say, red, green, blue, yellow, orange light in the visible spectrum, and then transmit. And then you can encode signals on all of them, and it becomes a bit like a light superhighway that allows it to get from point A to point B and get your message transmitted as well. And this becomes the core of how we're able to communicate all across the world. And with that, that is really the core of how a lot of the physics works and how we're able to communicate pretty much all throughout the world. And it becomes really the core principles of how communication works. So as always, if there are any questions, I'll be available to answer and see how it goes. Actually. So with that, it was a pleasure to be with all of you, and my apologies for stepping away for a minute. And, I hope to hear from you soon, and hope to see you next time.